Welcome to Equations of Motion Derivation. Today you will learn where the three most important equations in kinematics actually come from. These are not magic formulas to memorize, they flow directly from the definition of acceleration itself. By the end of this lesson, you will understand exactly why these equations have their shapes, and you will be able to derive them yourself if you ever forget them. Here are 4 facts that show you why equations of motion matter. A cricket ball dropped from a 100-meter building takes exactly 4.5 seconds to hit the ground. Most students guess 10 or more seconds, but physics gives the exact answer. Police accident investigators use these exact equations to figure out how fast a car was traveling before it crashed. Engineers use them to design safe braking systems for trains and cars. And the same equations that predict a falling ball also predict planetary orbits and comet trajectories. This is one set of equations that builds everything. Here are 4 facts that show you why equations of motion matter. A cricket ball dropped from a 100-meter building takes exactly 4.5 seconds to hit the ground. Most students guess 10 or more seconds, but physics gives the exact answer. Police accident investigators use these exact equations to figure out how fast a car was traveling before it crashed. Engineers use them to design safe braking systems for trains and cars. And the same equations that predict a falling ball also predict planetary orbits and comet trajectories. This is one set of equations that builds everything. Let me introduce the 3 golden equations. The first is v equals u plus at. This gives you the final velocity after time t if you start with initial velocity u and have constant acceleration a. The second is s equals ut plus 1/2 at squared. This tells you the displacement covered during time t. The third is v squared equals u squared plus 2 as. This is special because it does not involve time at all. You use it when you know displacement but not time. These 3 equations can solve almost every constant acceleration problem you will encounter. Now let us derive the first equation from pure definition. Acceleration is defined as change in velocity divided by change in time. So a equals v minus u divided by t. To solve for v, multiply both sides by t to get it equals v minus u. Then add u to both sides. You arrive at v equals u plus at. That is it. No magic, just algebra applied to the definition of acceleration. For the second equation, we use the fact that displacement equals average velocity multiplied by time. The average velocity over a time interval is the starting velocity plus the final velocity, divided by 2. So displacement equals u plus v over 2, times t. Now substitute v equals u plus at into this expression. The average velocity becomes u plus at over 2, which simplifies to u plus 1/2 at. Multiply this by t and you get s equals ut plus 1/2 at squared. Again, pure algebra from definitions. Here are all the key equations and what each one means. First equation, v equals u plus at, used when you know time and want final velocity. Second, s equals ut plus 1/2 at squared, used when you know time and want displacement. Third, v squared equals u squared plus 2 as, used when you do not know time but know displacement. And one more useful formula, displacement in the nth second equals u plus a times 2n minus 1 over 2. This is less common but appears in competitive exams. For your NEET exam, expect questions that give you 3 of the SVAT variables and ask you to find the 4th. Your key insight is learning to identify which equation avoids the variable you are not given. Remember the acronym SVAT, S is displacement, U is initial velocity, V is final velocity, A is acceleration, T is time. Most mistakes come from mixing up positive and negative directions. Choose up or forward as positive at the start and stick to that choice throughout. A common wrong answer comes from using the wrong equation or forgetting the 1/2 in the second equation. Let me summarize the 5 key takeaways. First, 3 equations connect all 5 SVAT variables. Second, these are not magical, they follow directly from the definition of acceleration. Third, they are valid only when acceleration is constant. Fourth, become skilled at choosing the equation that avoids the unknown variable you do not need. And fifth, always establish a sign convention and apply it consistently. This is where most mistakes happen. You now understand the derivation of the most powerful equations in kinematics.